In this lesson, we're going to learn about some inductive reasoning, all right? Inductive reasoning is all about finding patterns. So let's talk about a famous inductive reasoning problem. There once was a kid named Carl Friedrich Gauss that grew up to become a mathematician. And when he was a kid, he was kind of causing trouble in his classroom, being annoying to his teacher, something like that. And his teacher said, hey, go to the back of the room, be quiet, and add up the numbers 1 to 100. Teacher thought this would take him a little while. So Carl went back to the room for just a minute or two, or a few seconds, and came back and said, all right, here's the answer. And his teacher was amazed and said, whoa, how'd you do that? And I don't know, let's think about it. What do you think he said? He took these numbers, 1 to 100. Do you think he just added 1 plus 2 and said, hey, that's 3, plus 3 is 6, plus 4 is 10? Did he do that whole thing? Or did he have another way? Well, let's think about it. What if we pair these up a little differently? What's 1 plus 100? That's 101. What's 2 plus 99? That's 101. What's 3 plus 98? 101. 101. If we keep adding these up, we get 101. And if we keep going, we'll have 50 and 51 in the middle, and that'll be 101. So we get a whole bunch of 101s. In fact, how many 101s do we get? Well, we get 50 of them. All right, so we can see that we just have 50 times 101, and that's just 50, 5,050. So we can figure out difficult problems if we kind of notice some patterns. We think about what's going on, and we can answer things quickly. So that's what we want to do. We want to be able to solve problems quickly and efficiently. So let's think about this. First, we want to think about numbers so we can use them more carefully. We want to think about them in the way that the Greeks did in ancient Greece. The Greeks thought about numbers as shape. We've got numbers like a 1 by 1. Well, that's 1. We've got a 2 by 2. Well, that makes a nice square. 4. We've got 9, which makes a nice 3 by 3. We've got 16, which makes a nice 4 by 4. And so these numbers make some nice squares. They're square numbers, right? The shape of the numbers, as the Greeks would say, is a square. And we're familiar with this, right? The next one would be a 5 by 5. You don't need to draw it out, right? And 36, so on and so forth. So we can see that what's going on, this is 2 squared, this is 3 squared, this is 4 squared, so on and so forth. We see a nice pattern. And so if we wanted to jump to the 50th one, we don't need to draw it out. We just see that we're taking the square number, the building number, if you want to think of it that way, and we're multiplying it by itself. So this is going to be 50 squared, right? All right, so that's 2,500, and then we can come up with a rule. And we can say, well, if we have any number in, if we multiply it by itself or square it, we find the value of the square number. So that's not terribly new there. But what if we have other shapes? What if we talk about numbers that make an oblong number, or kind of a stretched out rectangle, or a stretched out square if you want? So if we have these numbers, now notice these buildings all have something in common. We've got a 1 by 2, 2 by 3, 3 by 4, so on and so forth. So how many numbers in the first building? Well, there's 2. How many dots, I should say? There's 2 dots. In the next building, there's 6. In the next building, there's 12. How many in this building? Well, there's 20. Do you have to count every single one to know there's 20? Probably not. We don't need to go 1, 2, 3, 4. We see there's 4 by 5, and there's 20. So if we want to keep building this pattern, we could keep drawing them, or we could think about how they're made. We have a 4 by 5. We have a 3 by 4. We had a 2 by 3. And we had a 1 by 2. So what's the fifth one going to be? Well, that's going to be a 5 by 6, right? And that's going to be 30. And the sixth one, well, that was going to be a 6 by 7, right? So we can see that without drawing them out, we can figure out how the pattern would continue. So if we look at small ones, we can figure out, well, what's the 50th one going to be? Again, we don't need to draw it out. We know it's going to be 50 times 51, right? And so that's going to be 2550. So what's going on? If we want to make a rule or a pattern here or a formula, we have n, the number itself. Notice that this always starts with 1, 2, 3, 4, 5, so on and so forth. So our rule or our pattern is going to start with n. Then, what are we going to multiply it by? Well, it's the number that's next to it. So what's right next door to n? Well, the number that comes right after n is one more, so we call that n plus 1. So 50 and 51, 100 and 101, so on and so forth. All right, so we got the square numbers and the oblong numbers. Well, there's some other numbers that are useful that can show up all the time in patterns, and those are called triangular numbers. Let's look at those. So triangular numbers are numbers that look like this. They make triangles. This isn't really a triangle. I guess you might even say it's a circle. But let's just call it a triangular number, all right? First one is 1. The next one, if we have like a pyramid kind of style here, but a flat pyramid, I guess, there's 3 in there, right? The third one, we've got a 1, 2, and a 3. That makes 6. The fourth one, 1, 2, 3, and 4. That makes 10, right? And the next one, we're going to add a layer of 5 to get the next one. And then we're going to add a layer of 6. That's going to be 21. Well, this is a kind of a harder pattern to see. We can see that we're going up by 2, up by 3, up by 4, up by 5, up by 6. But how are we going to get to the 50th one? Do we want to keep adding and adding and adding? Well, that's going to take a lot of time. So we need to find a connection. Well, the connection ends up being to the oblong numbers. So the oblong numbers are 2, 6, 12, 20, 30, 42. Okay, and we got those, remember, from 1 times 2, 2 times 3, 3 times 4, 4 times 5, 5 times 6. So do you see a pattern between the red oblong numbers and the blue triangular numbers? Yeah, hopefully we do there. The oblong numbers are twice as big as the triangular numbers. Or if we say this the other way around, we divide by 2 to get from the oblong numbers to the triangular numbers. So whenever you see triangular numbers, make a row or a column that is twice as big, and that will help a lot. So, well, this one's going to be 50 times 51, right? The 50th one, and that's the 50th oblong number, 2550. How do we get from the red numbers to the blue numbers? Well, we're divided by 2, right? So this is 1225. So our pattern is this. So for n, our rule, I should say, we're having n times n plus 1. That gives us the oblong numbers. How do we get to those triangular numbers? Well, we're going to take that oblong number and we're going to cut it in half. So our rule for our triangular numbers is n times n plus 1 divided by 2. There we have it. So now we got a rule for triangular numbers. All right, well, one more kind of numbers that shows up a lot. Triangular numbers show up all the time. Once again, the key, when you see triangular numbers, double them, okay? So if you see triangular numbers, double them. And then you'll find the pattern a lot easier. All right? So how about powers of 2? One more group here. This shows up a lot, especially in our digital age here. So look at our numbers here. We've got 1 in the first group. We've got 2 in the next group. We've got 4, then couple 4s, and then a couple 8s. So we've got 2, 4, 8, 16. What's happening? Can you see that we're doubling every time? So every time we're multiplying by 2, right? We're doubling, 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 all right? Now we can keep doubling, but this number is going to grow real fast, and we want to be able to jump to maybe the 100th number or whatever. So we need a rule, a formula here. So this is 2 to the first. This is 2 to the second. This is 2 to the third, 2 to the fourth, 2 to the fifth, and 1, remember, is 2 to the 0. So there's a connection here. 1 goes to 2 to the 0. 2 goes to 2 to the first. The third goes to 2 to the second. Fourth, 2 to the third. Fifth, 2 to the fourth. 6, 2 to the fifth. So how are we finding the exponent? Can you see that we're subtracting 1? And that's all that we're doing. So this is going to be 2 to the 9th. 2 to the 9th is 512. And so we're going to have our formula here. Our rule is 2 to 1 less than n. Well, what's 1 less than n? That's n minus 1. So there's our rule there. And those are called powers of 2. They show up in lots of different problems. So we can use these now whenever we want to find patterns. So when we're looking for patterns, we'll use something called the wishful thinking method, which is another name for inductive reasoning. So when we have a tough problem, it's important to wish for an easier problem, like fewer numbers, fewer steps, fewer items. Then make a table and solve those easier problems and look for a pattern. And then use that pattern to find the original answer to the original problem. So let's try this out on a couple. So here's a good number. We want to find the sum, find the sum of the first 100 even natural numbers, starting with 2. Well, that means take 2 plus 4 plus 6 plus 8 plus 10 plus 16, blah, blah, plus 200. That's a lot of numbers to add up. So that's a big problem. So wish for an easier problem. I don't want to add 100 numbers up. I just want to add one number up. So what if I add the first even number up? Well, that adds to 2. All right. What if okay, that was too easy. Let's get a little more challenging here. So let's add the first 2 even numbers. 2 and 4, the first 2 even numbers. 2 plus 4 gives us a sum of 6. What about 2 plus 4 plus 6? I think we can handle that. Well, that's 12. 2 plus 4 plus 6 plus 8, that's add 4 numbers, 20. And how about one more? 2 plus 4 plus 6 plus 8 plus 10, that is 30. Now, if we look at these numbers and think about what we quickly talked about there, these numbers look familiar. These are our oblong numbers. This is 1 times 2. This is 2 times 3. This is 3 times 4, 4 times 5, 5 times 6. So we got a pattern. So it's the number times one more. So these are the oblongs. We recognize that, and that tells us we have n times n plus 1. Okay? So we can do the same thing for adding the first 100 odd numbers. And why don't you try this number? You can pause this real quick and try it. Add the first 100 odd numbers. What do you get? And then what if we wanted to find the final digit of 4 to this big old power? Well, we could think of what's 4 to the first? What's 4 to the second? What's 4 to the third? So on and so forth, and find that last digit and see what happens. Try it out. So pause that video if you haven't and try it out. Think about that. And then I'll give you the answers. Hit play and you'll see the answers here. Now I realized here that actually we didn't finish this last one. What about, so we can use this. We got our n times n plus 1. And then we have for 100 numbers, well, that'd be 100 times 100 plus 1, 101, which 10100. Okay, so we got to have that there. All right, and then for the odd natural numbers, you get, when you add one number you get 1, two numbers you get 4, three numbers you get 9, so on and so forth. And these are just square numbers. And so in squared is our formula. You want to add 100 of them? Well, that's 100 squared, which is 100, also known as 10,000. Okay, and the final digit for 4 to, what is that, 87 millionth, blah, blah, blah. Well, we're going to find those powers. And when we find those powers and just look at the last exponent we get, or last digit, we get these. 4, 6, 4, 6, 4, 6. Do you see the pattern? Well, every even one is a 6. Every odd power ends in a 4. So what's this? It's an even power. So the last digit is going to have to be 6. I don't know what the whole thing is. Your calculator won't even tell you, but the last digit is 6. So that's how we use patterns to solve bigger problems. All right? So that's inductive reasoning using the wishful thinking method. Wish for an easier problem and find the pattern. So go be problem solvers, find the patterns, and solve the world's problems.